let's say you have been given an array. An array has some numbers, let's say 5, 2, -7, 4, 11, -20. This is your array A. We call another array a prefix sum array of A if PA of I is equal to sum of all the elements from A0 to AI. So this is 0, 1, 2, 3, 4, 5. Now, if I have to write prefix sum array of this array A, then you can visualize that at 0th index, what value are we going to keep?
5.
5. Yeah, because first element is sum of its own. Second index?
7.
7. Third index?
0.
0. So going forward, if you actually try to see, we can express prefix sum recursively in the sense, we can say if you know prefix sum of I minus 1, that means if you know these much values already, then ith prefix sum can be computed by adding a of I to it. That means if I have to fill the next value, it can be simply 0 plus 4, which is 4. What will be the next value?
15.
15, basically 4 plus 11. What will be the next value?
-5.
-5. So basically, if you are given an array A, we can recursively define prefix sum as PA of 0 is going to be A of 0. That's the base case. And PA of I is going to be PA of I minus 1 plus A of I. And if I give you array A and ask you to compute or calculate or work out another array PA, what will be the time complexity in which you can fill PA array? From array A, if you have to build another array PA, what will be the time complexity of doing so?
Big of n.
-1.
Yeah, it will be n minus 1 if you say like I'm just copying A0 here and then I'm running a loop from I is equal to 1 to n minus 1 and use this formula. So loop is running n minus 1 times. So that way, if you see it is n minus 1, if we just focus on loop iteration, if we count there is one extra assignment we have done prior to the loop, we can call it big of n. So I'm just skipping n minus 1 to writing it n. Okay. Or in shorter, if we have to create a prefix sum array, can I also start from I is equal to 0, I less than n, I plus plus? And can I also say if I is 0, we will say PA of I is equal to A of I. Otherwise, we will say PA of I is equal to PA of I minus 1 plus A of I. Then kind of we are running one loop to compute the full prefix sum array. And here you have A given to you and your A is given and you are creating PA. Now there are few advantages that prefix sum array provide us. There are certain problems that we can solve efficiently once we have prefix sum array, or if we think in the direction of prefix sum array. So let's take an example array and discuss one problem so that we understand the application of this. So I'm giving you an array A is equal to, let's say -1, -1, 1, 1, 1, -1, -1, 1, -1 and 1. So what do you observe about this array? What is special about this array?
contains only two types of numbers,
Yes,
1 and
it
minus 1.
contains only two types of numbers, which are ones and minus ones. Now, question is, what we have to do is we have to count all subarrays whose sum is 0. And subarrays are nothing but they are contiguous part of the array. Subarray is a contiguous part. You cannot leave elements in between. This is a contiguous part of the array. So if you look at above array and you talk about subarrays, if I just ask you, how many subarrays start at index 0? How many subarrays start at index 0?
9.
9, because first subarray is starting at 0, ending at 0. Second is starting at 0, ending at 1. So it is about this subarray, then this subarray, then this subarray, then this subarray, and continue to do. So it will all go up to 0 to 9. Now, if I ask you, starting from just 0, tell me which all subarrays have some 0.
Sir, 0 to 3.
0 to 3 is 1. Okay. So 0 to 3
0 to 5.
1. 0 to 5 is another whose sum is 0.
0
0
to
to
7.
7.
0 to 7 another subarray.
0 to 9.
9 also.
0 to 9 also. So all done. So that means starting at 0, we have 4 subarrays. Same way, if I ask you, subarray starting at 1, tell me subarray starting at 1 whose sum is 0.
1 to
1 to 2.
1 to 6.
1 to
1
6.
to 6.
1 to 8.
1 to 8. So total 3. Same way, let's go and find how many subarrays start at index 2 and give you a sum of 0.
2 and 8.
To 8. If you go from 2 to 8, just see how many ones are there in that, how many minus ones are there.
9.
It won't.
9.
Is it going to give from 2 to 8 or 2 to 9? Are you really going to get a sum of 0?
No.
Not possible, right?
Yes.
Okay, starting at 0, there is no subarray possible. Sorry, starting at index 2, no subarray possible. What about starting at index 3?
3 and 6.
3 to 6,
3 to
we
6.
have.
And 3 to 8 also.
3 to 8.
We have 3 to 8 also. Okay, 3 is done. Starting at index 4?
4 to 5. 4 to 7.
4 to 5 you have. 4 to?
4 to 7. 4 to
7.
9.
4 to
9 also.
4 to 9 also. Okay. Next, starting at index 5.
No subarray.
we don't have any.
We don't have. Starting at index 6.
6,
6
7,
to 7,
6,
6, 9.
6, 7, 6, 9.
6, 9.
Starting at index 7.
7,
Only
8.
7, 8.
10 to
Starting at index 8.
8, 9.
8. 8 to 9.
Okay, so we actually looked at each subarray to count, and total, what do you think? What is the number we got total? How many subarrays are having some 0?
16.
So everyone got this answer, 16? Now, if we have to solve this problem for an array whose size is up to 10 to the power 5, we are talking about this category of problem. And whatever we did just now, if you pay attention to that, it was just like a brute force approach where we are going and evaluating every subarray. And if I ask you, like I asked you earlier, subarray starting at index 0, starting at 0, there are total n subarrays. Do you agree with me on this?
Yes, sir.
Yes, sir.
Yeah, starting at 0. Starting at 1, how many subarrays?
N minus 1.
N minus 1. Starting at 2,
N minus 2.
starting at last index,
1.
1.
1 subarray. If you add all of them, total
N into
subarray-
n plus 1 by 2.
total subarrays are n into n plus 1 by 2. And out of these total subarrays, we are finding what meet our criteria. Okay. So this brute force that we talked about, this idea that we talked about, if we actually had to go and convert that into code, for subarrays, we know there is a starting point, there is an ending point. That is how we represented all the subarrays. So one way, if we have to do that, let's say, now see if n is of volume 10 to the power 5, the total number of subarrays goes 10 to the power 5 into 10 to the power 5 plus 1 by 2. It goes outside the int range if you just talk about multiplication. So we will take the return type to be long. Subarrays with 0 sum. And let's say we have, I'm writing it like a pseudocode. So this is A that is given to us, and we have to count the subarrays. So approach that we took just now, we said we will take for every start index from 0 to A dot size minus 1. This is our start index. Same way, for every end index, where did our end index start from? When we are looking at a subarray,
from I.
from S.
Yeah.
Here it is S to A dot size minus 1. So you got an S, you got an E. Now you can do a sum. You can do a sum for K is equal to S to E. You can take a sum. Initially sum is 0. You can say sum plus is equal to A of K. This inner loop is calculating sum of one subarray for which you know start and end. Now, can I say after this loop is over, you are going to say if sum is 0, we will do count plus is equal to 1. And this is our count. Is this clear? This is the pure brute force approach for counting subarrays.
Yes.
Yes. What will be the time complexity of this? Yeah, what is the time complexity of this?
NQ, size of AQ.
Yeah, so outer two loops, if you talk about, we just now discussed that they are going to generate unique S and E combinations are n into n plus 1. And if worst case, if you say this is n, bigger wise, yes, it will be n cube. Otherwise, you are doing n into n plus 1 by 2 subarrays. And inside, you are finding sum of each subarray. So this is into size of the subarray. Now we just do an approximation. We say size of maximum subarray will be n. So when we go and say bigger wise, we call it is n cube. And space complexity wise, we are not using any extra space. We are just using SE, sum, and C variable. 4 variables used. So that is big of 1. Now this is very naive brute force approach. This can be optimized. Somehow we can cut down this loop. We can make it n square easily by cutting down this loop. What we could have done? When outer loop gave us S, for S is equal to 0 to A dot size minus 1. We could have declared sum here. Sum is 0. The inner loop when E is varying from S to A dot size minus 1. Here, we could have directly said sum plus is equal to A of E. So if you see, currently we included just current element. It is like you are starting at index 0. Initial subarray you got is this. You got a sum. Then when you expand here, add one more element. When you expand here, add one more element. Now this is your first value of sum. This is second value of sum. This is third value of sum. As you are expanding in the inner loop, you can continue to get the sum. And here itself, if we check, if sum is 0, directly do count plus plus. And in the end, finally, we can return the count. If you see this versus previously we had unnecessary additional loop, which was computing the subarray sum. And this code is actually, you can call like here we are expanding the subarray and we are carrying the answer. Expanding subarray and getting the answer. So this approach, the second approach that we are seeing here, what is the time complexity of this? This time it is n into n plus
N square.
n square. And space complexity is 1. Okay. Although we have two very naive solutions, but will they really beat these constraints? Will n square pass? Will n
No,
square?
No, sir, because
it will cross the 10 power 8 iteration.
It will cross the 10 power 8 iterations boundary. More than 10 to the power 8 iterations give us TLE. So we need a better solution. We need an optimized solution. Okay. So in order to get its optimal solution, let's try to think in terms of prefix sum. What I want from you is help me write the prefix sum array for this array A. You see the array given below. I want you to help me with prefix sum array. What will be at index 0?
Minus 1.
Minus 1.
At index 1?
0.
Minus 2.
Minus 2.
Index 2?
1. Minus 1. Minus
Plus
1.
1.
Index 3?
0.
0.
Index 4?
1.
Minus 1.
Index
1.
5?
0.
0.
Index 6?
Minus 1.
Index 7?
0.
0.
Index 8?
Minus 1.
Index 9?
0.
Okay, so we have to make certain observation on the prefix sum array and see can we really now count the subarrays whose sum is 0. Now, if I ask you a question, wherever you see a 0 value, what can we conclude from that?
We already got subarrays. 4 subarrays.
And which are those subarrays?
0 to
0
3,
to
0
3,
to 5,
0
0
to
to
3,
7,
0
0 to
5,
9.
0
0 to 3, 0, 5, 0, 7.
Yeah, so at least starting from index 0, whatever had direct prefix sum 0, those you are able to directly observe from this 0 value. So far we got 4 subarrays. Now there were some other subarrays also, which kind of would have started from somewhere in the middle and reached somewhere. So like this kind of subarrays we are missing. Let's see how we can get those subarrays. If I ask you to make an observation about another point and say prefix sum array up to this point is -1. Prefix sum array up to this is -1. That means we are saying this to this prefix sum is -1. Now when you reach to the next -1, these additional things got added and you got this sum. So what is your conclusion about these dots, the numbers at these dots?
So after we get a -1, we are getting 0 in this subarray actually. So after we get 0 and we are going to the next sum, we are getting 1. So -1 and 1 get cancelled and we get 0 as the next sum.
Okay.
So we can conclude by moving forward or going backward and checking if there's a 0 or what's the value in the
Fair.
previous index.
Fair. If I call this index as R, if I this call index as L. What we are observing is, can I say we are seeing PA of L is equal to PA of R? This is our observation right now, that if two sums are same, then that is meaning PA of L is equal to PA of R. Now, L is less than R. That also we are seeing from here. If we try to correlate something from here, PA of L is nothing but A0 to P of 0 is P of L is representing A0 to. How did we calculate
P- A of L.
A of L? PA of R represents
A0 to AR.
A0 to AR. Can I say somewhere it will be AL minus 1 also? Somewhere it will be AL also. Somewhere it will be PA of A of R, sorry. Now, can I write PA of R as, this PA of R can be rewritten as, this overall thing that we have is PA of L plus, what is the additional range I have to add?
L to R.
L to R, are you sure? Is it L
L
to R?
plus 1 to
L
R.
plus
L
1
plus
to
1
R.
to R.
L plus
L
1.
is gone. This is L plus 1 to A of R. Now, PA of R is written as PA of R is equal to PA of L plus A of L plus 1 to R. And from our observation, if PA of L and PA of R are equal, if these two values are equal, what is your conclusion about this sum?
Like the subarray sum is 0.
This sum is going to be 0. Okay, that means if two indices are having same values, if you see here it was -1, here it is -1. So we are concluding after this, whatever subarray you have, look at original array. This subarray, what is the sum of this subarray?
0.
0. And you saw another -1 here. You had a -1 here. If you look at this subarray up to here, what is the sum of this subarray?
0.
That is also 0. You saw a -1 here, you saw a -1 here again. That means in between whatever numbers came, what is the sum of them? That is also 0. So any moment, let's talk about summarizing these two observations. First observation you said is, if a PA of I is 0, it means A0 to AI sum is 0. You found subarray has 0 sum. This is first category we saw earlier when we just observed all the zeros. Second observation we made is, if PA of L is equal to PA of R, what did we conclude?
The subarray sum is 0.
That
Like
means
the
AL plus 1 to
AR.
AR has 0 sum.
0.
Let's apply these two learnings and calculate the answer for this array again. Yeah, I will need this prefix sum array, guys. If you can remember it and let me know, I want to rewrite it. Yeah, so this array, help me rewrite below. Or let me see if you can zoom out and do that. Yeah.
-1, -2,
1, -1, -2.
-1,
Okay.
0,
Okay.
1.
0, 1, 0, -1.
Yes, sir. 0, 1, 0, -1. 0, -1, 0.
0.
-1, 0.
Okay. Yeah, guys. So this is what we have as a prefix sum array. Let's apply those two learnings and count. First of all, I'm not counting all the zeros. We will do that on the way. Let's look at this index. Let's start from index 0 in prefix sum array. So far, what should be the count of our subarrays?
1.
0.
0.
When you looked at -1, you want to know before -1, did you see another -1?
No.
No. So far sum remains 0. But at this moment, it will be valuable to know, hey, so far we have seen -1 one time, because in future, if we see another -1, this information will be helpful. Okay, so we are remembering this. So this is prefix sum. This is its frequency. So we are saying at index 0, we found -1 one time. Let's move forward. Now you came to index 1. This is prefix sum -2. Did we see -2 earlier?
No.
No. Okay, so count does not change, but we remember -2 is seen one time so far. Now you come to -1. Did we see -1 earlier?
Yes.
Yes.
How many times?
One time.
If we saw it one time earlier, that means how many subarrays are there whose sum is going to be 0? Our observation was this, right? 1. So we do the count as 1 because we have seen -1 earlier also. And before moving forward, we say, hey, now prefix sum -1 has occurred 2 times. Okay, let's come here. What is the prefix sum here?
0.
0. So 0 should tell us one subarray you can directly count. And at the same time also ask, did we see 0 earlier?
No.
No. So not seen. Now let's count. 0 is occurring one time. Come to next value. What is the value?
1.
1.
Did we see a prefix sum of 1 earlier?
No.
No. So no change in the count. And now we say 1 has been seen one time. Come to this 0. Whenever you say prefix sum 0, count should directly become 3. And next question to ask is,
Frequency.
did we see 0 earlier?
Yes.
One time. So what should be the change? The increment?
Frequency should be.
Frequency of 0 should change to.
And 0's frequency should change to 2. Yeah, there is somebody who is causing disturbance. Can you be on mute if you are not in a silent place? Yeah, please do not create noise. It disturbs others. Okay, so 0, since we had seen earlier, this 1 0 is telling this is a subarray. Another thing that this 0 should tell is previously we saw 0, so this is also a subarray. So this 0 is contributing to subarrays. And then we increment the count of 0 to 2. Okay, then let's go forward. We see a -1. Did we see -1 earlier? Answer to that is
Yes. Yes.
and we have seen -1 earlier how many times?
2
times.
times.
That means they should be contributing 2 subarrays. One is this, another is this. After that -1, whichever subarray comes. So that will give us the count of 4 plus 2, 6. And now -1 becomes 3 times. Come to another 0. When you see a 0, from index 0 till this 0, there is one subarray for sure. This 0 is coming after 2 other zeros. So how many subarrays in between we should have?
3.
2.
2,
3.
not 3. Not 3.
Total, please. Total.
After first 0 and after second 0, 2. This 0 we have already counted. Yeah. So 7 becomes 9. Now come to -1 again. Okay, for 0, I should increment its count to 3.
Frequency.
Yeah. Now come to -1. -1 has been seen earlier 3 times. So those 3 should get added. And now -1 becomes 4 times. Come to last 0. One increment directly because it is a 0. Another increment is how many times you saw 0 earlier. So 0 was seen 3 times earlier, so it becomes 16. Now, how can you keep track of this information? As you are moving ahead, this information What is the easiest way to keep track of this info?
Map.
Dictionaries.
Dictionary or map?
Map.
So basically, if you create a prefix sum array of original array, and after that you use dictionary and map, in one iteration, after building prefix sum array, in one iteration of this array, we are able to compute the answer. And previously, when we manually did answer computation, we came up with 16 subarrays. Okay, so yeah, this is the idea, like how we can make certain observation about prefix sum array and solve the problem. Hope this makes sense. This gives you idea of how prefix sum is applicable to solve certain problems efficiently.